This is Physics 2, Chapter 32, which will be dealing with particle physics. And this will be part 1 for the videos. So, we know with a regular atom that we have a nucleus that has protons and neutrons, and then we have orbits around it that contain electrons, and this makes up matter. We will see later that we have other particles that will deal with matter. We've actually seen one already, which would be a neutrino. But we also have antimatter, which is pretty much the opposite here. Instead of protons and neutrons in here, you have anti-neutrons, which I put a little line above it to indicate anti, and anti-protons, which are negative in charge. And then you have the idea of I'm not even going to make an orbit because it's not necessarily like that, but you have positrons on the outside. And then you also can have anti-neutrinos, which we've seen already as well. And this would be a V with a line above it, well, this is just a V. And anti-neutrinos, they have basically the reverse of the neutron. Now, a neutrino doesn't have a different charge, but there is what's called a baryon number that we'll go and get into, and that's opposite for a neutron and an anti-neutron. The antiproton has an opposite has an opposite charge, so it's negative instead of proton, just like the positron is positive instead of negative. And so this is all consistent of antimatter. Right, so there are also other particles that are their own antiparticle. So we have the photon and the Higgs particle and the pion, and these are all their own antiparticle. So if we look on this, we have for hydrogen, you have an up quark, which we're going to get into, another up quark and a down quark, and this makes up a proton. There's no neutron for this one, and then you have the electron moving about it. For the anti-hydrogen, you have a anti-up quark instead of an up quark. You have another anti-up quark instead of an up quark, and you have an anti-down quark instead of a down quark. And this will make the anti-proton. And then you have a positron moving about it. And so this will be anti-hydrogen. Alright, so we're going to get into the fundamentals. And so we want to remember that we're going to be dealing with looking at both matter and antimatter in this. And which ones have antimatter and which ones do not. So first, for the fundamentals, and I'll start with matter, and then we'll have antimatter. First, we have 6 types of quarks. And then for antimatter, you have antiquarks. The 6 are up, down. These two are what make up a neutron and a proton. Then you'll have bottom, top, charm, and strange. And then these will be anti-up, anti-down, anti-bottom, anti-top, anti-charm, and anti-strange. And so we see with these different 6 quarks, the charge is 2/3 for an up and 1/2 spin, and it has a certain mass of 2.3 MeVs per c squared. The charm has everything the same charge, same spin, but a 1.275 GeVs per c squared mass. The top has 173.07 GeVs per c squared, but that also has the same charge, same spin. The down has a negative 1/3 and 1/2 spin, and 4.8 MeVs. Strange, 95 MeVs, and is also negative 1/3 and 1/2. And then the bottom is also negative 1/3 and 1/2, and that's at 4.18 GeVs. So these 6. So if we look at the, if we look at 2 ups and a down, we're looking at 2/3 charge, 2/3 charge, and negative 1/3 charge, since down is negative 1/3 and the up is positive 2/3. So this gives you 2, 4, and 3 out of 3, which gives you a positive 1. Okay. If we look at 2 downs and an up, you have negative 1/3, minus 1/3, plus 2/3. These are going to end up being 0. Right, so this is the makeup of a neutron. This is the makeup of a proton. And showing the charge equals what you see them as. Right. These quarks make up protons, neutrons, and then also what's called mesons. Okay. These 6 are the first 6 fundamentals. Let me erase this part of it. The next ones are what we call leptons. Okay. The biggest one that is, I guess the most common one, is electrons. And this is what makes up matter. And then over here we have positrons. Okay, still are leptons. And for the electron, it's 0.511 MeVs, negative 1 charge, 1/2 spin. So electron itself is a fundamental, where the proton and the neutron are not fundamentals. Right? Now this is the one that makes up matter. We also have within cosmic rays, so these are still leptons. So Then cosmic rays. We have muons. We have tau. And we have, as I said before, neutrinos. And we have over here anti-muons, anti-tau, and anti-neutrinos. Okay, the tau has a symbol of the tau. And of course the anti one has a bar above it. The muon has a symbol of a muon. And of course has a bar above it for anti. And then the neutrinos are V, or V with a bar above it. Right. There's three types of neutrons. Oh, I'm sorry, there's three types of neutrinos. And they're actually going to be easy to remember because they go right along with these three fundamentals. So we have the electron neutrino, which we'll label as V sub E, the muon neutrino, which we'll call V sub mu, and then the tau neutrino, which we call V sub tau. And then very similar, these will have, I'm not going to write out these, they're all anti, but anti electron neutrino, anti the tau, the muon neutrino, anti the tau neutrino. Okay, so those are the other ones. So with these, we are looking at 1, 2, 3, 4, 5, 6 more fundamental particles of matter, and then of course 6 more fundamental particles of antimatter. Right. So the muons decays quickly, and they will decay into an electron and two types of neutrinos. The tau can decay into what's called a hadron, which I'll get into. Can also decay into another lepton, which leptons are all electrons, muons, and the neutrinos. And it produces a tau neutrino during any decay, which is the tau neutrino is one of the flavors of neutrinos. And so we have the three types of neutrinos, and they do not interact with electromagnetic forces, so they don't have any charge. These leptons do not act with strong force. They do act with what's called the weak force. So leptons, we talked about strong forces before with protons and neutrons. That is not involved in leptons, but they do have weak forces pulling them together. And then leptons with charge also interact with the electromagnetic force. So, like for instance, electrons interact with electromagnetic forces. Now, electrons are -1 charge and half spin. Muons are -1 charge and half spin. Taus are -1 charge and half spin. And then neutrinos are 0. So really there's only two possible charges for a matter of leptons, -1 or 0. Antimatter, you're going to have charges of +1 for each of these, or 0. These are all -1 and 0 for neutrinos. And then we're going to get into the fact that these are going to have what's called a lepton number. And the antimatter will have the anti-lepton number. Right, so we went through now 6 different quarks and 6 different leptons. So we have 6 quarks that are fundamental, 6 leptons that are fundamental, and of course we have 6 anti-quarks, 6 anti-leptons. And we also have 4 carriers of force. And these are their own antiparticles. Right? So these include photons, gluons, and bosons. So the 4 that we have, the gluons, this is the carrier of the strong force. It's also the carrier of what we're going to call the color force, which this deals with quarks, and it's kind of a weird way of phrasing it. But you see what I mean when I get to it. The color is just basically a categorical name for it. Each quark carries a colored charge, and the force between the quarks is the color force. And it's a weird name for it, but when I get to it, I'll discuss it. The exchange particle between protons and neutrons is dealing with the strong force, which means you have gluons between protons and neutrons, kind of holding it together. Then we have photons. These are carriers of the electromagnetic force. Has 0 mass and causes the electromagnetic force to have a significant large range, and it moves at the speed of light. Then we have the W and Z bosons. These are carrier of the weak force. They have significantly large mass. So these actually do have mass. Well, these we didn't see any mass. And you see that we have the W boson over here is about 80.4 GeVs, while the Z boson is about 91.2 GeVs. The W boson you see has a positive and negative charge, while the Z boson does not. Right. So this large mass causes a short range for the weak force. The W boson is a mediator of neutrino emissions and absorptions, and it's the source in nuclear transmutations, like the nuclear decays. The Z boson, however, it mediates neutrinos interactions with electrons. Then we have the Higgs boson. This is an interaction with the W and Z bosons to slow them down. It is alleged to have been found in 2012, so it's relatively new, and it's assumed to be significant in why some fundamental particles have mass and some do not. Right, so we have 4 forces of our nature. Strong, we have gluons. Electromagnetic, we have photons. Weak, we have both the W and the Z boson. And then the gravitational force, we still don't have a field particle for that. Notice none of these included. So they named it the graviton, but they haven't actually found it. That's why there's a little question mark there. Right, so if they ever find it, we may have a 17th fundamental particle, but right now we don't know. Right now, all of these, I'll come back to this page here in a minute. I won't get down to the end of this. You're seeing the notes. I went too far. Right, well, I have the different leptons listed out. So electron, neutrino, positron, electron, antineutrino, anti-muon, muon, muon neutrino, muon antineutrino, and then I don't have all of them, but we have some of them listed out. I thought I had tau, but anyways, you can come to here and you see each of these, and there's a good way to have things listed together. And it just lists the mass, the charge, the baryon number, which we'll get into, the lepton number, which we'll get into. Notice all of these have a lepton number, none of these have a baryon number. And then the strangeness is also an important thing we'll get into. And none of them have it because none of them are made by quarks. Remember, the strange is a quark. And let's see, I have other tables here that we'll get into. Trying to see if they have more. Here's where the hadrons are. We're going to get into these as well soon. That includes the neutron and the proton. And then I have some here that would help try to distinguish which ones we have. So we have the leptons and we have the quarks up here, and the antiquarks and the antileptons. So I have some resources here for you to look at, even to just remember the names and remember the symbols with these. So you can kind of start getting an idea of how they are. Then with the fundamental particles, again, gauge bosons, Higgs boson, and then the different quarks and different leptons. And we have some more. Here's the fundamentals. So I do have the listed, each of them. This is each lepton number here, the baryon number, strangeness. So I do have the resources for all of the different fundamental particles somewhere in the end of this chapter, so you guys can find what you need as you need it within these tables. Alright, so I just want to point that out before we get into some more information. So let me see what time this is. 24 minutes. Okay. So I'm going to go through a little bit of this and then we'll probably start a new video here. Because we'll be dealing more with this stuff here soon too. With cosmic rays, we have high energy radiation coming in from the solar system. And so it originates outside of our solar system and is believed to come multiple sources including supernovas. So it comes from multiple types of possible sources that are sending these cosmic rays towards us. And this discovery of the cosmic rays have led to the discovery of these new types of particles. And high energy accelerators are now used to study these new types of particles. So by high energy accelerators, what we're looking at is these kind of particle accelerators we're going to get into. So the first thing, and I went into something with this earlier in one of the magnetic and electromagnetic chapters, but now we're going to really get into detail with this. So you have what's called a cyclotron, and the particles move between inside two D-hollow shaped sheet metal electrodes that are separated by a gap. That's what this is here. It is these D-shaped. I'm going to kind of draw this as a top view. And they're D-shaped, but one's going to be backwards D. One's going to be frontwards D. Alright, and these are middle hollow sheet metal electrodes. They're separated by this gap. And the electrodes is spaced, so there's a gap, and a voltage is going to be applied across this gap. So you're applying a voltage across this. As the particles move, so let's say this, I'll draw this in a different color. This is a particle that moves through. It would eventually reach the gap. When they reach the gap, they are accelerated through the gap onto the other side, and then they move again. Right? And as the particles pick up speed and increase the radius of curvature, so I should start closer inside, but this one will actually, you know what, let me kind of redraw this a little bit. I'll start a little smaller inside so I can have some space here. Okay, so let's start here. Comes through, and as it jumps, it accelerates. So it gets faster, and then it accelerates again. So it gets faster, and it accelerates again. So it gets faster, accelerates again, so it gets faster. Alright, and it continues and continues, and this here it uses the voltage to accelerate the particle. So it increases its speed, which increases its radius. The voltage must be what we call alternating, so that the positive particle accelerates to the negative side. And these particles must be in phase with the frequency of the voltage. So this voltage is alternating at some frequency. And this particle has to move, so when it reaches this gap, it's always in phase with it, and so it always is causing this particle to accelerate as it moves through. Because if it ever reverses, then it will slow this particle down and do the opposite of what you want. So you want the particle to reach that phase as soon as it's right in order to make it the jump and to accelerate through. But then once it reaches the other side, then the voltage has to switch. So it's accelerating through this, or moving through this D field back to the gap again. And so you need the voltage to be alternating. Eventually, these particles will reach the outer edge and head to a target. So at this point, you get to this outer edge and it heads to this target here, and you'll get this exiting beam from it. So within these electrodes, we have the magnetic force, which is QVB, and it's going to equal the force of the mass times velocity squared over r. This QVB is not changing, so as your velocity changes, your radius will change. Right, so the velocity itself is going to be QVB. Oh, you know what? Let me solve it out. We'll multiply the r over to the side, so we have Q VBR over equals mv squared. This v cancels that v, and so v equals QBR over m. Since we are having this move within this electrode, the time it takes to move through a complete revolution is going to be the circumference of this electrode, so 2 pi times the radius over that velocity. And so if we plug in the velocity, we get 2 pi r m over q b r. This m comes because that's in the denominator. So the radius can be cancelled. And so the time it takes is 2 pi times the mass over the charge times the magnetic field. And then the frequency is 1 over the period. So it's Q times the B field over 2 pi times the mass, or divided by 2 pi times the mass. And so we can find the frequency that we need for this electrode. Right, so we have some different particle accelerators here. We have cyclotrons. These are for relativistic particles, so particles going close to this, well, really high speeds, close to the speed of light. And so they have a frequency that depends on the speed. And so either the frequency or the magnetic field must change to match the speed of the alternating particles. Right, we have different laboratories here. CERN laboratory. This accelerates particles for research. And it has a large hadron collider, which we'll get into what a hadron is. But that was basically taking and producing protons and colliding protons together, or colliding proton beams together. So the two beams are produced in opposite directions. As they come through, they collide, and then whatever comes out of that is measured. These protons can have as much as 12 tele-eVs of energy when colliding, and the protons are moving at speeds of 3.1 meters per second slower than the speed of light. So it's still moving really fast. Still not as fast as the speed of light though. So this is another little picture of them zooming around and colliding. Alright, so they have 7 experiments at this CERN laboratories that they do in order to get as many measurements as they can. One's the compact muon solenoid. Its purpose is to hunt for the Higgs boson, which has been found though, but I'm sure they still want to make measurements with it. And then it looks for clues to dark matter. And so these are just, this is kind of an overall picture of that kind of machine that they use to experiment, to do this experiment. And then this is kind of a little diagram sketch of it. We have what's called an ATLAS. This is general purpose detector. Measures a broad range of signals in order to detect anything that may be produced. You can see how big it is compared to that guy. And it has different components: muon detectors, a magnetic system, an inner detector, and calometers to make its measurements. Then we have the LHCb. This is a specific purpose detector. It measures the hadron containing the bottom quark and tries to investigate what happens to the rest of the antimatter. We have what's called ALICE. This is a specific purpose detector as well. Studies a form of matter called quark gluon plasma. So this one is the ALICE, and what it looks like. This is again a diagram of it and then the actual picture of it. And then we have small detectors with specific purposes. The MOEDAL searches for a magnetic monopole. The TOTEM measures diffractive processes, elastic scattering, and total cross sections of the particles. And the LHC forward measures the energy and numbers of neutral pions produced in a collider. Right, so a lot of different experiments on these. Then we have the Stanford Linear Accelerator Laboratory. This, as you can see, this is really long. And how long they have needed in order to speed these particles up, and then they, one goes this way and one goes around in this red direction and collide here at the detector. So this is a linear accelerator. So the idea with this is as this moves forward into a as it's in a positive positive section of this linear path, when it reaches this gap, with it we're dealing with, I think, protons going through. I just want to make sure. No, electrons, I'm sorry. So electrons are accelerated. When it reaches this gap, you want this side to switch over to be positive, so it accelerates towards it, and then reaches this side and switches over to be positive, and reaches this side and switches over to be positive. So whenever it reaches the end right before the next gap, you want the gap in front, the section of the tube in front of it to be positive, so it accelerates forward. And notice these get longer as you move through, and the reason why is because as it speeds up, it needs more length before that switch happens, so they can time it just right. And I guess sometimes they use positrons as well, so they may have this switched over. And it can accelerate electrons or positrons up to 50 GeVs of energy. The voltage is applied using, again, an alternating voltage, so these switches just at the right time. Very similar to the way I kind of described it here. And then the subjects of the particles is oscillating electric potential that will increase the particle's kinetic energy. So as it moves through, it's increasing its speed and increasing its kinetic energy. And then the voltage oscillates, so the tube in front of the electron is always positive, and the tube the electron left is negative at every gap. That is the main way this works. Like I said, the size of the tube have to increase due to increasing speed of the electrons. And they have to be just the right length to stay in phase with that oscillating voltage. This linear collider here collides electrons and protons to the center of mass of 90 GeVs. Collisions are head-on and achieve high energy. They use this to study the Z boson. The Z bosons are detected by the large detector specifically designed there to measure them. And then in order to get high resolution, the faster a particle moves, the greater the momentum of the particle. The higher the momentum results in what we have will be a shorter wavelength. So when this is high, this wavelength will be short. And then the shorter wavelengths have a higher resolution. So that's why they have to speed everything up so they can have a shorter wavelength and better resolution in measuring these. Okay, so the next video I'm going to start with composite particles. I'm going to end this video, and I will see you in the next video.